guys, this is Mrs. Gastler, and in this video we are going to talk about simple harmonic motion of a mass on a spring. It's going to be fun. So let's get to it. So there's going to be two cases that we're going to talk about with the mass on a spring, because there's two different situations that this could happen on. And in our first one, we're going to talk about horizontal mass on a spring, and that is when a mass is moving across a horizontal surface like a table or a track, and the spring is attached to one side. Although in some really complicated situations you might have a different spring on the other side or the same spring, so that it's vibrating in between those. And in this situation, let's pretend that this is my equilibrium and that I can pull my mass over here, maybe like a ghost mass over here, and then when I let go it goes back this way and squishes the spring, and then that spring pushes it back this way, and then it just keeps going back and forth like this. Okay, so it might come back like this, okay, like that. And so the mass then is just going to go back and forth across the surface. In order for this to really work, this is going to have to be frictionless. Okay, and often the problems that you're going to see are going to be on frictionless surfaces, which is useful. In this case, for this simple harmonic motion, our restoring force, remember, for simple harmonic motion, our restoring force has to be directly proportional to the displacement and in the opposite direction. I'm going to abbreviate direction, opposite direction. And in this case, that is exactly true, because this time it is it's that spring force. And you might remember we just did this one, Hooke's law is what we're talking about. And so that is F equals minus KX. And there's that opposite, and there's that direct proportion. Directly proportional. Okay, so it is definitely in the opposite direction, and it is definitely directly proportional. And so it is definitely simple harmonic motion. So it's always going to be pushing or pulling that M back toward that equilibrium point. Okay, and so that's how we would figure that one out. So with our period, remember that's going to be measured in seconds, and it is a capital T. It has a very similar format. And again, it takes a little bit of calculus to be able to figure this one out, which we don't have. So we're not going to be using calculus, but it's 2 pi square root of m over k. Okay, so remember a pendulum is 2 pi square root of L over G. Okay, this one is 2 pi square root of m over k. 2 pi L over G, m over k. So they have very similar formats. And so does the frequency. So remember, frequency is curly f, 1 over the period. Okay, so and that one is going to be per second, or a hertz, which is Hz, hertz. Okay, and so when we do 1 over 2 pi square root of m over k, m, we get 1 over 2 pi square root of k over m. And that has the same format of what the pendulum looks like. The pendulum is 2 pi square root of g over L. I gotta be honest, I don't remember if the frequency ones are on there, but the period ones are definitely on the equation sheet for you. Okay, so let's talk about energy and a mass on a spring. With our pendulum, we had it swinging back and forth. And remember, in order for a pendulum to be considered a simple harmonic motion, it can't have a big angle, because that angle depends on the sine of theta, which only really works as a direct proportion for very small angles, which is less than 30 degrees. And so, but it works. I mean, we could pull this guy as far as we want, as long as we don't stretch the spring out, right? Because the spring is going to get deformed just like a paper clip does. Okay. The energy considerations here work just a little bit differently. So the kind of energy that we're dealing with is not gravitational, because it's just staying at one level, so we don't have to worry about gravitational potential energy here. So when we have it at the ends, it's not going to be moving, so we would have no kinetic energy. So our total energy would be kinetic plus the spring potential energy, but there's no kinetic energy here. Okay. In the middle, where it's at that equilibrium value, the potential energy of the spring is now 0. So it's going to have all potential energy, or I'm sorry, all kinetic energy, because all it is moving. So maybe we could draw some whooshy lines as it moves across there. And the velocity is squared, so it doesn't have a positive or a negative value. The displacement is squared. Remember, the spring potential energy is 1/2 kx squared, so there's no negative value there either. So there's no negative value in either of these, so it's always going to have a positive value for the energy. Over here it is stopped again, so we go back to having no kinetic energy and only the spring potential energy. And then back again here, it's moving the other direction, and we go back to having kinetic energy but no spring potential energy. Okay, so it might look something like this. On a bar graph, that would have our, if we could watch the bars move, the bars would go back and forth, back and forth this way, transferring back and forth between the kinetic and the potential energy. Okay, spring potential energy. In reality, this surface is probably not frictionless, and so energy is going to be lost due to friction. And that's going to cause it to move slower in the middle and not move quite as far. And eventually it's going to come to rest at the equilibrium position. Okay, and so that is something to note. When you watch if you were to watch like the sine curve that it makes, it would just get smaller and smaller. Interestingly enough, since there's nothing about the position in either of these formulas, well, the period or frequency formulas, M and K, that's not going to change the period. Okay, the spring constant is still the same and the mass is still the same, so the displacement does not show up in there anywhere. The amplitude doesn't show up in there anywhere. The speed doesn't show up in there anywhere. So as it slows down with this dampening, the frequency and the period do not change. Maybe you should make a note of that. F and T don't change as that happens. Okay. With forced vibrations, just like in the pendulum, where you can have something that gives it a little push every now and then to keep it swinging, you could have the same thing happen here, although I don't see an obvious place where you would do that. You might have to have it in the mass that's on the spring. It might have to have like a little motor in it that gives it a little push, a little battery, a little spin or something to get it to keep moving along that spring there. Something to give it a push. There's some noise in the hallway. Something to give it a push to keep going. So that it doesn't lose energy to spring. You can also give it a push to get it going faster or slower or farther or something like that. But since the period is dependent on the mass and the spring constant, you're not going to increase its period or its frequency unless you change the mass or the spring constant. Okay? So maybe you can make it have a higher amplitude instead. Okay? So let's look at case 2, and this one's going to be fun. Case 2 is the vertical one, the vertical mass on a spring. Okay, and so when I start off with a spring hanging here, it's going to have some, what we like to call a rest length or an unstretched length. Okay, and when I hang a mass on it, it stretches down to some distance, and this is my new equilibrium. Okay, and then when I give this a little tug downward, my mass, and I let go, my mass will go up and down and up and down. It's loads of fun. They actually have things like this that are decorations for your like front porch. Okay, you can have like a frog or a flower or some random things that hang on your front porch that you could do this with, which are loads of fun. Okay, and they will sit there and bounce up and down. It's loads of force, loads of fun. Okay, so it's vertical, so that's the first difference. Okay, really? Difference. Okay. My restoring force is actually still the spring. The spring force. Okay. You might want to think that it has to do also with gravity. And interesting things happen that make the gravitational force not actually matter. So I'm going to put a little star here and write that gravity doesn't matter. And we'll talk about that here in a second. The period is still 2 pi square root of m over k, and the frequency is still 2 pi square root, 1 over 2 pi square root of k over m. And the energy is also exactly the same. It's k and, plus the U spring. And so you might be thinking right now, what? Why don't I have to include things about gravity? Gravity. Gravitational potential energy doesn't matter. Okay. And so I'm going to give you two options here. Option one, you can take my word for it and stop the video. It doesn't matter. You can pretend that gravity doesn't exist. The force of the spring is your restoring force. All the calculations work out. All of the energy calculations work out. You do not have to include gravity in here. Or you can keep watching. You can watch this derivation. It's a proof, okay? Some people like proofs and some people don't. If you like proofs, watch this proof, okay? It's up to you. Okay, so I drew the spring already, but I'm going to draw it again right here so that I have it for a reference. Okay, so here's my spring that is unstretched. Let's say this unstretched length, well, let's call this, for right now, we'll call this 0, okay? And I'm going to hang a mass on it, and that's going to stretch it down here, and let's call this distance that it's stretched A, okay? And I'm going to give it a pull. Actually, right here, this is at equilibrium. So when it's right here, the net force is 0. And what I can get from that is that, what do you call it? Kx, the spring force on it, has to be balancing out mg. Okay? And so if I wanted to find out how far A is, okay, because of this right here, I know that this distance A, okay, if I plug A in for x, k times A is mg, and then I can solve that for A. That distance A is mg over k, okay? So in terms of values that I can know, this spring constant k, and m, whatever m I hang on here, and g. So those are values that I could potentially know. I could determine this A in terms of crap I can know, right? Or things that I'm given, okay? Now, let's say that I like to pull on things, and I give this thing a little tug, and now I pull it down to here. So you can imagine my hand there. I have just pulled it down. That's not the best looking hand here. Let me give myself a wrist, okay? There, I'm wearing a watch. Yeah, because I like watches, okay? So that's me pulling it down, okay? Now this distance that I have pulled it down is from this is the new equilibrium, right? Okay, is B. Okay. Now, depending on how hard I pulled on it, we could figure out what that is, or we might be able to have that information. But right now, I'm really more concerned about the energy considerations instead of what I'm actually doing, and I want to pick that out. Now, what people really like to do in physics is they like to pick things that are going to be easy. And so I'm going to pick this to be our initial spot, and I'm going to let go of this thing, and I'm going to look at the energy when I get right up here back to this equilibrium. So I make that be my final spot, okay? The initial and final spots are right here. And also because physicists like to be picking things that are easy, I'm going to move that 0, and I'm going to say, you know what, this is the best 0. So this is going to be where my height is 0, and that means that mg times h is 0 right at this initial line. Okay. So, according to the conservation of energy, the initial energy equals the final energy. So, what do I know about the initial energy? Well, right here, it's right here, it isn't moving, right? Okay, even if I'm not letting go, or as soon as I let go, it hasn't started moving yet, but it's about to, right? It's going to start doing that acceleration but at time 0, v equals 0, and then at time 0.0000 next, right? It starts moving, but it hasn't started moving yet. So the kinetic energy plus the gravitational potential energy plus the spring potential energy, and the same set of things for the other side, but I didn't write them in the same order, and it's fine, okay? So there's no kinetic energy, right? It's at this 0 mark, so there's no gravitational potential energy. So the only spring potential energy that I have to worry about is that's all that I have to worry about. Okay. Now, since it was originally here and now it's here and now it's there, it's 1/2 times k times a plus b squared. Because that's the whole distance that it's been stretched, right? Here all the way down to there is what it is. Okay. And so on the other side, my F is this middle line right here. So my spring potential energy there is 1/2 k. It's only at A right now, so A squared. And then my G, my UG is mg, and it'll be, let's see, from 0, it's at B, okay? And then K will be 1/2 mv squared, however fast that happens to be. So now we just have to do some fun algebra. So first we're going to FOIL this guy out. So let's see. That's a squared plus 2ab plus b squared. This junk is all going to stay the same, so I'm just going to leave that there. So then this is 1/2 ka squared plus, let's see, the 1 and the 2 cancel out, so that's kab plus 1/2 kb squared. And then what I'm going to do is I'm going to take this thing, and, well, here, let me back up a second. Ka squared plus mgb plus 1/2 mv squared. Okay, so right now this and this cancel out. Now I'm going to stick this in there, okay? So I'm going to do, actually the k's are going to cancel out, so I'll just leave it there. K times mg over k times b. Goodbye k's. So that's going to be mgb plus 1/2 k, leave the k, b squared equals mgb plus 1/2 mvb squared. Mgb cancels out. I get 1/2 kb squared equals 1/2 mv squared. I'm going to put little dots. These means, which is what I was trying to show. Right here. Oh, look. UG canceled out. What I've actually shown is that US at B equals K at A. So what this means is if I put the equilibrium point, oops, I didn't finish the word. If I put the equilibrium point, wow, I can't spell this morning, point at the 0 for my spring potential energy, then the math works. Okay? Ta-da! All right. Go forth, 2 questions. Have fun.